what those different values mean last time in reference to the probability of a type 1 error. At the 1% level, the data do support that a linear association exists between, the age and advertised price of used Toyota Corollas. Okay, and this piece here is why we didn't cover regression back in chapter 3. Up to this point, how have we been deciding if there's an association? We've been looking at the scatter plot. It's been a subjective decision. Something that looks like an association to me may not have looked like an association to you. We just kind of made a judgment call that there seemed to be a pattern. Now, in our defense, many of the examples we've looked at have been strong associations. So it's been fairly obvious that yes, something is going on. The correlation coefficients tended to be close to 1 or -1. But what if you had a correlation coefficient of maybe 0.4? In some instances, that could be kind of strong. But if you visually looked at the scatter plot, you may not see it as being an association. So if you need to decide, is there an association that I can really dig into, make predictions from, use the simple linear regression? One of your first steps will be evaluating the hypothesis test for the slope. Because this is telling you, or giving you some information about, whether or not there is an association between your variables. So before you make any predictions, hopefully you're supporting the alternative hypothesis. You have a p-value less than whatever the level of significance is that you've chosen. Making predictions when there's no association is silly. Practically what you're saying is you have a flat line. So no matter what your x is, your y value will be the same. It doesn't change as x changes. So there needs to be an association before you start making predictions, interpreting intercepts, interpreting slopes, etc. Okay, so check this before you really dig into things. So a final note. Yeah, and I'm at about an hour and 8 minutes, so it's definitely a lot shorter. So the other remaining time on Thursday, probably not for the whole 40 minutes or whatever will be left in this lecture, but some large portion of Thursday's lecture. We'll go through StatCrunch and we'll look at some more examples of regression, how to do it, things to look out for, how to make the interpretations. We'll work through some more together. But as I mentioned before, I encourage you to go ahead and try that. Go to StatCrunch, go to the groups, go to the student data sheet, or even the exam 1 data, and pick 2 quantitative continuous variables, make a scatter plot, try to make a visual judgment of if there's an association, run the simple linear regression, and look at the output. See if it makes sense. How would you interpret all of those pieces? Can you replicate what we've done here? Okay. So the last thing to mention, and we've talked about this a couple of times, is you should not blindly regress data. You have to look at it. You should do what we did here. Look at things one variable at a time. Do you have any unusual values within each variable? What are their distributions? What's the scope of the data? What do they look like together? Take the time to learn about the data. Look at it. If it seems like there's an association, if it seems like there's something to learn from, then jump into linear regression. Don't just take two data sets or two variables and try to regress them. That is a recipe for disaster. Apart from there not being an association, what can happen is if you don't really understand your data, you're going to extrapolate. And this happens all the time. At NIOSH, we have generally every summer, but for the past summer or two, we've had the same two interns, and they're pretty smart. They have master's degrees too. They're recent graduates. All of the time, they're extrapolating. You cannot do that. You cannot make predictions beyond your data. It's really easy to fall into the trap of just running mechanically through these processes that we've been working on, using t-test in the calculator. Find the function, type it in, get the p-value, etc. That's easy. Anybody can do that. What you need to do is think about the details, the why. Why am I doing a t-test? What are the assumptions? Are those being met? Do my results make sense? In terms of regression, is there something to regress? Is there some relationship to learn about? If so, cool. But you can only make predictions, you can only learn where you have data. Now, there are methods for extrapolation. So, for example, in time series analysis, you want to make predictions into the future, say weather forecasts. They're making a prediction beyond the data. There are tools to do that. Linear regression is not the one, generally the one for that task. Sometimes it's okay, but for the most part, be wary of extrapolating. Stay within the data. Okay? That's pretty much the lecture. So an hour and 11 minutes, an hour and 12 minutes, a little bit shorter. Hopefully it was okay. Hopefully you can see. Hopefully you can hear. Thursday we'll kind of recap this. We'll do some more examples. And we'll proceed as usual. So see you then.